In Lesson 7.1, we're going to look at exponential models, the graphs of exponential functions, and then simple interest equations. The basic equation of an exponential function is f of x equals a times b to the x. We know that f of x can also be written as y, so you might see it as y equals a times b to the x power. And a couple important things about our equation. B is known as the base number. B has to be bigger than 0, so it has to be a positive number. And B cannot equal 1. If you have 1 to some power x, that's still just equal to 1, and that gives you a horizontal line, not an exponential graph. So B cannot equal 1, and it's bigger than 0. X is always the exponent. That's what defines an exponential equation. Right, so I've given a couple examples here of what the graphs can look like. The first one is an exponential growth model. It's when b is bigger than 1. An example would be y equals 2 to the x power. A growth model on the left-hand side starts close to y equals 0. It doesn't actually touch it, it just gets infinitely closer the further to the left. As you travel towards the right of the graph, you can see here where it exponentially gets larger, and it infinitely would go on to the right. An exponential decay function is when b is between 0 and 1. b has to be bigger than 0, but less than 1. An example would be y equals 1/4 to the x power. On the left-hand side, we start infinitely large. It decreases rapidly, and then as you approach y equals 0, it gets closer and closer, but it will never actually touch that line. This line at y equals 0 is known as the asymptote. An asymptote is a line the graph approaches, but will never actually touch. It gets infinitely closer, but never touches. So let's try graphing these on our own. We're going to graph the function y equals 3 to the power of x, and we're going to use a table of values. The 3 points that I want you to use for x are -1, 0, and 1. Let's put these in for the x of my equation. So y equals 3 to the -1st power, 3 to the 0 power, and 3 to the 1st. Last chapter we learned a little bit about exponents. Any negative exponent will take what's in the numerator and divide it or drop it into the denominator. Anything to the 0 power is equal to 1, and 3 to the 1st is equal to itself. So the points that I'm going to plot are -1, 1/3, 0, 1, and 1, 3. Right, let's draw up the xy coordinate system. Draw out our points. -1 to +1, go up 3 spaces. So for accuracy, I want you to get it below the half mark, but not touching 0. That's my -1, 1/3, 0, 1, and then 1, 3. The basic shape of my graph, on the left-hand side, it approaches y equals 0, my asymptote. Going through my different points, you'll see a rapid increase, which creates the exponential graph, and it can go infinitely on up. So this was an exponential growth model. B was greater than 1, and I can see it forms the right graph. Right, let's try one now with an exponential decay, where b is less than 1. The basic shape is it starts high on the left-hand side and will decrease rapidly, approaching 0 on the right. Let's put up our table of values for x and y. X would be -1, 0, 1. Fill them in for the y value. I get 2 times 1/5 to the -1st. You have to do the exponent first. This is not 2 times 1/5. You have to do 1/5 to the -1st. So you take the 5, the negative exponent moves it to the numerator. It's 2 times 5, which is 10. To the 0 power, 1/5 to the 0 is 1, so I get 2 times 1. And to the first power, 2 times 1/5 is 2 over 5, or 0.4. All right, let's graph our points. Okay, I went ahead and plotted out the 3 points, bringing my x and y pairs together. I plotted -1, +10, 0, 2, 1.4, and I can see that my graph forms the basic shape of exponential decay. All right, on letter C, I want you to go ahead and give that one a try. Push pause while you do your work, and then resume play to check your answer. This was the solution that I came up with. My points were -1, 0.10, 0, 0.5, and 1, 2.5. Plotting them, I can see this was exponential growth. My b value was bigger than 1, so it matches up. Right, in our next set of problems, there's no graphing involved. We just need to understand parts of the equation. So without graphing, determine whether it represents growth or decay, and then find the y-intercept. So to recap, exponential growth is when your b value is greater than 1. Exponential decay is when it's between 0 and 1. And our y-intercept is when x is equal to 0. So let's look at that for a moment. When x is equal to 0, let's put it into our basic equation of y equals a times b to the x. So I'll have y equals a times b to the 0. Well, anything to the 0 power is 1, even if it's the variable, and 1 times a is just a. So my y-intercept is always going to be whatever number is next to your base. And I want us to write it as an ordered pair, so it'll be 0, comma, a. All right, let's apply these to our next problem. I look for the base, 1/3. 1/3 is less than 1, so I know this is a decay model. And for my y-intercept, I locate that number that represents the letter A, 0.99. So my y-intercept is at 0.99. On letter B, I locate my b value, which is 5 over 4. 5 over 4 is greater than 1, so this is a growth model. For my y-intercept, locate that a value and write it as an ordered pair, 0, 185. Okay, go ahead and try letter C. Push pause while you work and then resume to check your answer. So I had the b value was greater than 1, making it a growth model, and my y-intercept is at the point 0 and 0.25. And our last example for this lesson, we're going to work with interest, with money, money. Simple interest. Our formula for that, A equals P times 1 plus r to the power of t. Going through what each variable means, A is the money, the total money. Let's write that. A is equal to the total money. P stands for the word principal, which is the money that you start with. For example, if you put money into a savings account, the principal amount is what you put into the account. Letter A is the amount after you've earned interest after so many years, that total amount in the bank account. R is your interest rate, and it needs to be in decimal. And T is your time, and it needs to be in years. So let's see how this equation applies in our problems. You suppose you deposit $1,500. That's the money you put into the account, so that's the letter P. It pays an interest of 6%. So for R, you're going to put 0.06. No money is added or withdrawn from the account. How much will there be after 5 years? So time is 5 years. Put each value in and calculate A. 1,500 times 1 plus 0.06 to the 5th power. And just type that right into your calculator. Go. I typed it into the calculator and I got $2,007.34. Right, go ahead and try letter B. The only thing that changes is how much time the money is in the account. Push pause and do the work. Then when you're ready, resume to check your answer. Plugging all the values in, the only thing that changed was 20. I got $4,810.70. And that concludes lesson 7-1. Thanks.